Hello! So this is a supplement to our normal videos where I want to talk a little bit about the mathematics of calculating the cross product. This is something that you may have had a lot of experience with, you may not have had a lot of experience with, you may have covered it in a pre-calculus class or a calculus class, but I don't want to assume that everybody is experts with cross products, and after all, they're one of the sort of more complicated, at least conceptually, mathematical tools that we're going to use. Right, integrals we can think of as Riemann sums, derivatives or slopes, but cross products are really something that's really different. The way that I think of cross products is by thinking about how perpendicular are two vectors. Okay, so if two vectors lie somewhere in three-dimensional space, I might be interested in knowing how parallel they are, and that's sort of a measure of the dot product. The scalar product, has that cosine theta in it, and so the dot product tells me how aligned are two different vectors. Whereas the cross product kind of tells me, well, how perpendicular are they? So the more perpendicular something is, the greater the magnitude of the cross product. But it also gives me information about direction, because the result of a cross product is a vector. And so the result of the cross product has both this idea of magnitude, which corresponds to how perpendicular, and direction, which tells me the relative orientation of the two vectors. So mathematically speaking, a cross product is a function. It takes in two vectors, and I'm going to use the two that we're interested in. I'm going to call them v and b, but it could be any two vectors. And it returns a vector that is perpendicular to both v and b. Okay? A cross product takes in two vectors and it returns a vector. And there are three ways of calculating it. And I'm going to do all three ways with you on this video. But because I want to restrict I want to restrict conceptually what we're doing, I'm going to simplify one of my vectors. So I'll take the vector v to be arbitrarily in three dimensions. It's going to have an x component, vx, a y component, and a z component, vy and vz. But I'm going to say that that b, the magnetic field, but just the b vector in this case, is just going to be in the z direction. Okay, this is going to make the mathematics look a little bit simpler, but it's going to conceptually encompass everything that I need to know about the cross products. After all, if I have freedom to choose my coordinate system, I can always choose one of the axes to lie along one of the vectors that I'm interested in, and so maybe that's justification for doing it this way. Everything I'm saying here quickly expands to the case where B has three different components. There's more algebra there, and I think it messes up it makes the argument look a little bit messier. Okay, so way number one is the conceptual way of calculating a cross product. So I have my force is proportional to the cross product of v and b, and so I need to calculate what is the cross product of v and b. As vectors, oftentimes we find ways to do this by first calculating the magnitude of the vector and then dealing with the direction of the vector separately. So that's what way number one is. I'm going to calculate the magnitude of this cross product, and then I'm going to assign direction to it. So I calculate the magnitude of the cross product by finding out how perpendicular are these two things. So now theta is the angle between the two vectors. So v is pointing one way, b is pointing the other way. Theta is the angle between them. And the magnitude of the cross product of v cross b is the magnitude of v times the magnitude of b times the sine of the angle between them, not the cosine. So if two vectors are parallel to each other, then theta goes to 0 and sine theta goes to 0, and the magnitude of the cross product also goes to 0. So if I plug that into my expression for the force, then the magnitude of the force is the magnitude of Q, magnitude of V, magnitude of B, sine of the angle between V and B. Okay? And that's something that I can calculate straightforwardly, right? I can calculate all of these magnitudes. And note, I put the magnitude around Q as well because I'm looking for the magnitude of the force, and therefore I need something that's going to be strictly positive because I'm going to deal with the direction on the next with the next step. Okay, so now we have to talk about the direction of the cross product. The direction of the resultant of the cross product is given by what we call the right-hand rule. Okay? And for this, in order to do the right-hand rule, you are going to need your right hand. Okay. Now it's important that you use your right hand. Some of you are right-handed, and so you will have an inclination to try to be writing while you do your left hand, while you do your rule with the left hand, and that's always a mistake. It's actually more common that right-handed people make this mistake because they end up writing while trying to do the right hand rule. Okay. You can't do that. If you need to do the right hand rule, put your pencil down. Lay your left hand firmly on the table and raise your right hand so that you're not confused. Okay? And now once you have your right hand out, there are actually two common ways of doing the right hand rule. The first one is, and I'm going to turn to the side so that we're sort of looking in the same direction. The first one is to take your fingers and to point them in the direction of the first vector, and then curl your fingers in the direction of the second vector, and then your thumb will naturally point in the direction of the right-hand rule. Will give you the resultant of V cross B. So if my first vector is pointing up and my second vector is pointing to the left, then the resultant is going to be pointing directly towards me, and that's the result of the right-hand rule. If the first vector is pointing into the board and the second vector is pointing to the right, then the resulting vector is pointing down. Okay? And that's how that was one way of getting the direction of the right hand rule. Now the second way of using your right hand to get the direction is the way that I prefer, and that's because it helps me not to confuse which vector is which. And with curling my fingers, sometimes I forget where I started, and as you rotate your arm around, which is a necessary thing to do while doing the right hand rule, sometimes you forget where you started. So what I like to do is take my first finger for first vector, and point it in the direction of the first vector. So let me say it's up in the air. You can then rotate your wrist sort of arbitrarily around that first vector, and that's going to be important because you take your second finger and point it in the direction of the second vector. So if the first vector is up and the second vector is to the left, I can do this by pointing my first vector my first finger in the direction of the first vector, rotating to the second, and now I can see both of those vectors with my two fingers. And I can also, if they're not exactly perpendicular to each other, I can adjust my second finger so that it takes any angle between 0 and 180, but it can't do more than that, right? Because if it's more than that, I have to flip my hand around. But if I'm crossing up with left, then my thumb automatically points in the direction of the right hand rule. Okay, so that's the second way of using your right hand to get the direction of the right hand rule. Now, of course, the direction of V cross B isn't always the same as the direction of F, right? Because when I'm doing it conceptually, I have to worry that if I calculate V cross B and Q is less than 0, then the direction of F is going to be opposite the direction of V cross B. So the right-hand rule for V cross B gives you the direction of the force on a positive charge. But if I have a force on a negative charge, then I have to flip that direction. Some people will say, if there's a negative charge, use the left-hand rule. Do not use the left-hand rule. Do not ever use the left-hand rule. There is no such thing as the left-hand rule. There's only such a thing as the opposite of the right-hand rule. Way number 2, which is an interesting way, is actually to use components. And now this is sort of the standard. This is the gold standard way of doing right-hand rules because it is always going to work. If you can write down two vectors in terms of components in any coordinate system, then you can calculate the right-hand rule using components. But what you need is the definition of all of the cross products of individual components. So a right-handed coordinate system is defined such that x cross y is z, y cross z is x, and z cross x is y. That is, all of my cardinal directions have well-defined cross products. If I switch the directions of any of these two, then I switch the direction of the cross product, right? We saw this when I flip my hand around. If the cross product, if I switch the order of the two inputs of the cross product, I get an anti-symmetric answer, right? I introduce a minus sign into the answer. But my coordinate system comes with a definition that we agreed upon that says that this is the relationship between the different unit vectors. How I remember it is to draw this little recycling symbol where I draw x, y, and z, and then I draw arrows between them. And then I know that if I do x cross y, I'm flowing along the arrows, I get z. But if I do y cross x, I'm flowing against the arrows, and I get z minus z. So if I take that and I apply it to the problem at hand, I can see that I'm taking f is equal to v cross b. I can write out v in terms of its components and explicitly cross it with z. I can distribute that cross product into the sum, and then I have things that look like x cross z, y cross z, and z cross z. And now I can go back to my table and I can find out what all these cross products are. X cross z is minus y cross z is x, and z cross z is 0 because they're parallel to each other, and therefore the sine of the angle between them is 0, and that doesn't contribute at all. Okay, and then I'm left with an expression that gives me the cross products in terms of the unit vectors. And of course, this has no magnitudes, right? And so if q is less than 0, this is automatically going to take into account that the force is in the opposite direction than what you're given by the right-hand rule. This is the gold standard of doing it. This is how it always works when I'm confused about cross products, or if I'm doing cross products and I'm not getting an answer that makes sense. This is what I always go back to. At the same time, it's the most algebraically intense, because if I have 3 components in each of my cross products, I'm going to have a lot of terms that I have to calculate. I mean, it's a little bit intimidating, but it's reassuring that we'll always get the answer right. And lastly, there's another way, which is really a mathematical simplification of the component way. If I have Cartesian coordinates, I can keep track of all of the different non-vanishing cross products by writing the cross product as the determinant of this funny matrix, where the first line of the matrix is the unit vectors. The second line of the matrix is the components of the first vector. And the third line of the matrix is the components of the second vector. Okay? So it goes unit vectors, first vector, second vector. And if I take the determinant of this, then I get the cross product. So in the case that I'm interested in, where I'm eliminating 2 of the components of b, and that makes this last component just b0, then I can expand the determinant by minors, and I very quickly get the answer to the cross product. And I say very quickly because it so happens that if you evaluate a determinant by minors and you only have one row or one entry in one of the rows, then you only have to do a 2x2 determinant, and the problem ends up being very fast. Okay, this is not always the case, right? If I have 6 unknowns, or if I have 6 components that I know, then evaluating this determinant can actually be something rather complicated. Okay, so this is not always going to save you time, but if you're in Cartesian coordinates and you have vectors that are easy to calculate, it's a very common way of calculating the cross product.